Magnesium is a chemical element with symbol Mg and atomic number 12. It is a shiny gray solid which bears a close physical resemblance to the other 5 elements in the second column of the periodic table. They each have the same electron configuration in their outer electron shell, producing a similar crystal structure. Magnesium is the 9th most abundant element in the universe. It is synthesized in large, aging stars from the sequential addition of 3 helium nuclei to a carbon nucleus. When such a star explodes as a supernova, much of its magnesium is expelled into the interstellar medium, where it can be recycled into new star systems. Consequently, magnesium is the 8th most abundant element in the Earth's crust and the 4th most common element in the Earth, making up 13% of the planet's mass and a large fraction of the planet's mantle. It is the 3rd most abundant element dissolved in seawater, after sodium and chlorine. Magnesium only occurs naturally in combination with other elements, where it invariably has a +2 oxidation state. The free element can be produced artificially, and is highly reactive. The free metal burns with a characteristic brilliant white light, making it a useful ingredient in flares. The metal is now obtained mainly by electrolysis of magnesium salts obtained from brine. In commerce, the chief use for the metal is as an alloying agent to make aluminium-magnesium alloys, sometimes called magnesium or magnesium. Since magnesium is less dense than aluminium, this alloy is prized for its properties of lightness combined with strength. Magnesium is the 11th most abundant element by mass in the human body. Its ions are essential to all cells. They interact with polyphosphate compounds such as ATP, DNA, and RNA. Hundreds of enzymes require magnesium ions to function. Magnesium compounds are used medicinally as common laxatives, antacids, and to stabilize abnormal nerve excitation or blood vessel spasm such as in eclampsia. Magnesium ions are sour to the taste, and in low concentrations they help impart a natural tartness to fresh mineral waters. Magnesium is the metallic ion at the center of chlorophyll, and is a common additive to fertilizers. Characteristics: physical properties. Elemental magnesium is a gray-white lightweight metal, 2/3 the density of aluminium. It tarnishes slightly when exposed to air, although, unlike the other alkaline earth metals, an oxygen-free environment is unnecessary for storage because magnesium is protected by a thin layer of oxide that is fairly impermeable and difficult to remove. Magnesium has both the lowest melting and the lowest boiling points of any of the alkali earth metals, at 923 K and 1363 K, respectively. Magnesium reacts with water at room temperature, though it reacts much more slowly than the similar earth alkali metal calcium. When submerged in water, hydrogen bubbles almost unnoticeably begin to form on the surface of the metal, though, if powdered, it reacts much more rapidly. The reaction occurs faster with higher temperatures. Magnesium's ability to react with water can be harnessed to produce energy and run a magnesium-based engine. Magnesium also reacts exothermically with most acids, such as hydrochloric acid. This reaction with hydrogen chloride produces the chloride of the metal and releases hydrogen gas. Chemical properties. Flammability. Magnesium is a highly flammable metal, especially when powdered or shaved into thin strips. Once ignited, it is difficult to extinguish, being able to burn in nitrogen, carbon dioxide and water. This property was used in incendiary weapons used in the firebombing of cities in World War II. The only practical civil defense being to smother a burning flare under dry sand to exclude the atmosphere. Magnesium may also be used as an ignition source for thermite, a mixture of aluminium and iron oxide powder that is otherwise difficult to ignite. Source of light. Upon burning in air, magnesium produces a brilliant white light that includes strong ultraviolet. Thus, magnesium powder was used as a source of illumination in the early days of photography. Later, magnesium ribbon was used in electrically ignited flash bulbs. Magnesium powder is used in the manufacture of fireworks and marine flares where a brilliant white light is required. Occurrence see also. Category: Magnesium minerals. Magnesium is the 8th most abundant element in the Earth's crust by mass and tied in 7th place with iron in terms of molarity. It is found in large deposits of magnesite, dolomite, and other minerals, and in mineral waters, where magnesium ion is soluble. Although magnesium is found in over 60 minerals, only dolomite, magnesite, brucite, carnallite, talc, and olivine are of commercial importance. The Mg2+ cation is the second most abundant cation in seawater, which makes seawater and sea salt an attractive commercial source of Mg. To extract the magnesium, calcium hydroxide is added to seawater to form magnesium hydroxide precipitate. MgCl2+ California 2 Mg2+ CaCl2 Magnesium hydroxide is insoluble in water, so it can be filtered out and reacted with hydrochloric acid to obtain concentrated magnesium chloride. Mg2+ 2 hydrogen chloride MgCl2+ 2H2O from magnesium chloride. Electrolysis produces magnesium. Forms. Alloy. As of 2013, magnesium alloy consumption was less than 1 million tons per year, compared with 50 million tons of aluminum alloys. Its use has been historically limited by its tendency to corrode, high temperature creep, and flammability. Corrosion. The presence of iron, nickel, copper, and cobalt strongly activates corrosion. Reducing the quantity of these metals improves corrosion resistance. Sufficient manganese overcomes the corrosive effects of iron. This requires precise control over composition, increasing costs. Adding a cathodic poison captures atomic hydrogen within the structure of a metal. This prevents the formation of free hydrogen gas, which is required for corrosive chemical processes. The addition of about 0.33% of arsenic reduces its corrosion rate in a salt solution by a factor of nearly 10. High temperature creep and flammability. Research and development eliminated magnesium's tendency toward high temperature creep by inclusion of scandium and gadolinium. Flammability was greatly reduced by introducing a small amount of calcium into the mix. Compounds. Magnesium forms a variety of industrially and biologically important compounds, including magnesium carbonate, magnesium chloride, magnesium citrate, magnesium hydroxide, magnesium oxide, magnesium sulfate, and magnesium sulfate heptahydrate. Isotopes. Magnesium has 3 stable isotopes: 24 megagrams, 25 megagrams and 26 megagrams. All are present in significant amounts. About 79% of Mg is 24 megagrams. The isotope 28 megagrams is radioactive and in the 1950s to 1970s was made commercially by several nuclear power plants for use in scientific experiments. The isotope has a relatively short half-life and so its use was limited by shipping times. 26 megagrams has found application in isotopic geology, similar to that of aluminium. 26 megagrams is a radiogenic daughter product of 26Al, which has a half-life of 717,000 years. Large enrichments of stable 26 megagrams have been observed in the California Al-rich inclusions of some carbonaceous chondrite meteorites. The anomalous abundance of 26 megagrams is attributed to the decay of its parent 26Al in the inclusions. Therefore, the meteorite must have formed in the solar nebula before the 26Al had decayed. Hence, these fragments are among the oldest objects in the solar system and have preserved information about its early history. It is conventional to plot 26 megagrams, 24 megagrams against an Al per megagram ratio. In an isochron dating plot, the Al per megagram ratio plotted is 27 Al, 24 megagrams. The slope of the isochron has no age significance, but indicates the initial 26 Al, 27 Al ratio in the sample at the time when the systems were separated from a common reservoir. Production. China is the dominant supplier of magnesium, with approximately 80% of the world market share. China is almost completely reliant on the silicothermic pigeon process to obtain the metal. The process can also be carried out with carbon at approx 2,300 degrees Celsius. 2 MgO plus C plus 2 Cow 2 megagrams plus California 2 CO4 MgO plus CMg plus CO. In the United States, magnesium is obtained principally with the Dow process, by electrolysis of fused magnesium chloride from brine and seawater. A saline solution containing Mg2+ ions is first treated with lime and the precipitated magnesium hydroxide is collected. Mg2++ Cal plus H2O California 2++ Mg2. The hydroxide is then converted to a partial hydrate of magnesium chloride by treating the hydroxide with hydrochloric acid and heating of the product. Mg2 plus 2 hydrogen chloride MgCl2 plus 2 H2O. The salt is then electrolyzed in the molten state. At the cathode, the Mg2+ ion is reduced by 2 electrons to magnesium metal. Mg2++ 2E- Mg at the anode. Each pair of Cl- ions is oxidized to chlorine gas, releasing 2 electrons to complete the circuit. 2Cl-Cl2 plus 2E- A new process, solid oxide membrane technology, involves the electrolytic reduction of MgO. At the cathode, Mg2+ ion is reduced by 2 electrons to magnesium metal. The electrolyte is yttria stabilized zirconia. The anode is a liquid metal. At the YSZ, liquid metal anode O2- is oxidized. A layer of graphite borders the liquid metal anode, and at this interface carbon and oxygen react to form carbon monoxide. When silver is used as the liquid metal anode, there is no reductant carbon or hydrogen needed, and only oxygen gas is evolved at the anode. It has been reported that this method provides a 40% reduction in cost per pound over the electrolytic reduction method. This method is more environmentally sound than others because there is much less carbon dioxide emitted. The United States has traditionally been the major world supplier of this metal, supplying 45% of world production even as recently as 1995. History. The name magnesium originates from the Greek word for a district in Thessaly called Magnesia. It is related to magnetite manganese, which also originated from this area, and required differentiation as separate substances. See manganese for this history. In 1618, a farmer at Epsom in England attempted to give his cows water from a well there. The cows refused to drink because of the water's bitter taste, but the farmer noticed that the water seemed to heal scratches and rashes. The substance became known as Epsom salts and its fame spread. It was eventually recognized as hydrated magnesium sulfate, MgSO47H2O. The metal itself was first produced by Sir Humphry Davy in England in 1808. He used electrolysis on a mixture of magnesia and mercuric oxide. Antoine Bussy prepared it in coherent form in 1831. Davy's first suggestion for a name was magnium, but the name magnesium is now used. Uses as a metal. Magnesium is the third most commonly used structural metal, following iron and aluminium. It has been called the lightest useful metal by the periodic table of videos. The main applications of magnesium are, in order: component of aluminium alloys, in die casting, to remove sulfur in the production of iron and steel, and the production of titanium in the Crawl process. Magnesium is used to create super-strong yet lightweight materials and alloys. For example, when infused with silicon carbide nanoparticles to gain extremely high specific strength. Historically, magnesium was one of the main aerospace construction metals and was used for German military aircraft as early as World War I and extensively for German aircraft in World War II. The Germans coined the name electron for magnesium alloy. The term is still used today. The application of magnesium in the commercial aerospace industry was generally restricted to engine-related components, due either to perceived hazards with magnesium parts in the event of fire or to corrosion. Currently, the use of magnesium alloys in aerospace is increasing, mostly driven by the increasing importance of fuel economy and the need to reduce weight. The development and testing of new magnesium alloys continues, notably Electron 21, which has successfully undergone extensive aerospace testing for suitability in engine and internal and airframe components. The European Community runs 3 R&D magnesium projects in the Aerospace Priority of 6 framework program. Aircraft Wright Aeronautical used a magnesium crankcase in the World War II era Wright duplex Cyclone aviation engine. This presented a serious problem for the earliest examples of the Boeing B-29 heavy bomber, as engine fires in flight could ignite the engine crankcases, literally torching the wing spar apart from a combustion temperature as high as 5,600 degrees Fahrenheit. Automotive Mercedes-Benz used the alloy electron in the body of an early model Mercedes-Benz 300 SLR. These cars ran at Le Mans, the Mille Miglia, and other world-class race events in 1955. Porsche used magnesium alloy frames in the 917 053 that won Le Mans in 1971, and continues to use magnesium alloys for its engine blocks due to the weight advantage. Volkswagen Group has used magnesium in its engine components for many years. Mitsubishi Motors also uses magnesium for its paddle shifters. BMW used magnesium alloy blocks in their N52 engine, including an aluminium alloy insert for the cylinder walls and cooling jacket surrounded by a high-temperature magnesium alloy AJ62A. The engine was used worldwide between 2005 and 2011 in various 1, 3, 5, 6, and 7 series models, as well as the Z4, X1, X3, and X5. Chevrolet used the magnesium alloy AE44 in the 2006 Corvette Z06. Both AJ62A and AE44 are recent developments in high-temperature low-creep magnesium alloys. The general strategy for such alloys is to form intermetallic precipitates at the grain boundaries, for example by adding mesh metal or calcium. New alloy development and lower costs that make magnesium competitive with aluminium will increase the number of automotive applications. Electronics. Because of low weight and good mechanical and electrical properties, magnesium is widely used for manufacturing of mobile phones, laptop and tablet computers, cameras, and other electronic components. Other magnesium, being readily available and relatively non-toxic, has a variety of uses. Magnesium is flammable, burning at a temperature of approximately 3,100 degrees Celsius, and the auto-ignition temperature of magnesium ribbon is approximately 473 degrees Celsius. It produces intense, bright, white light when it burns. Magnesium's high combustion temperature makes it a useful tool for starting emergency fires. Other uses include flash photography, flares, pyrotechnics, and fireworks sparklers. Magnesium is also often used to ignite thermite or other materials that require a high ignition temperature, in the form of turnings or ribbons, to prepare Grignard reagents, which are useful in organic synthesis, as an additive agent in conventional propellants and the production of nodular graphite in cast iron, as a reducing agent to separate uranium and other metals from their salts, as a sacrificial anode to protect boats, underground tanks, pipelines, buried structures, and water heaters, alloyed with zinc to produce the zinc sheet used in photo engraving plates in the printing industry, dry cell battery walls, and roofing. As a metal, this element's principal use is as an alloying additive to aluminium, with these aluminium-magnesium alloys being used mainly for beverage cans, sports equipment such as golf clubs, fishing reels, and archery bows and arrows. Specialty, high-grade car wheels of magnesium alloy are called mag wheels, although the term is often more broadly misapplied to include aluminium wheels. Many car and aircraft manufacturers have made engine and body parts from magnesium. Safety precautions: magnesium metal and its alloys are explosive hazards. They are highly flammable in the pure form when molten or in powder or ribbon form. Burning or molten magnesium metal reacts violently with water. When working with powdered magnesium, safety glasses with welding eye protection are employed, because the bright white light produced by burning magnesium contains ultraviolet light that can permanently damage the retinas of the eyes. Magnesium is capable of reducing water to highly flammable hydrogen gas, Mg plus 2H2O Mg2 plus H2. As a result, water cannot extinguish magnesium fires. The hydrogen gas produced only intensifies the fire. Dry sand is an effective smothering agent, but only on relatively level and flat surfaces. Magnesium also reacts with carbon dioxide to form magnesium oxide and carbon. 2 megagrams plus CO2 2 MgO plus C. Hence, carbon dioxide fire extinguishers are also ineffective for extinguishing magnesium fires. Burning magnesium is usually quenched by using a Class D dry chemical fire extinguisher, or by covering the fire with sand or magnesium foundry flux to remove its air source. Uses in compounds. Magnesium compounds, primarily magnesium oxide, are used as a refractory material in furnace linings for producing iron, steel, non-ferrous metals, glass, and cement. Magnesium oxide and other magnesium compounds are also used in the agricultural, chemical, and construction industries. Magnesium oxide from calcination is used as an electrical insulator in fire-resistant cables. Magnesium reacted with an alkyl halide gives a Grignard reagent, which is a very useful tool for preparing alcohols. Magnesium salts are frequently included in various foods, fertilizers, and culture media. Magnesium sulfite is used in the manufacture of paper. Magnesium phosphate is used to fireproof wood used in construction. Magnesium hexafluorosilicate is used in moth-proofing of textiles. In the form of turnings or ribbons, Mg is useful in purification of solvents, for example the preparation of super-dry ethanol.